Okay, welcome back everyone to biostatistics. So today we are going to continue on the chi-square test. So you have learned about the goodness of fit test under chi-square, and now we are going to continue on the chi-square independence test. So you apply chi-square independent test when you have two categorical variables from a single population. So unlike the goodness of fit test, you only have one categorical variable. Like for example, you wanted to know whether if male and female have a ratio of 1 to 1. So you only have one categorical variable, which is your gender. But for chi-square independent test, you have two categorical variables. And you need to use chi-square to determine whether if there is a significant association between these two variables. So you will have your data in a contingency table. So what is a contingency table? It's a cross-tabulation table. So it's a matrix table where you can have a 2 by 2 or 3 by 3 or 2 by 3. So it depends on the example given. So for example, so I draw it out over here where you can have a 2 by 2, like for example, female and male, again smoking and non-smoking. So what you wanted to know from here is that whether if the behavior of smoking is dependent on gender. So this is there'll be a 2 level in category for gender and 2 level in the category for the smoking behavior. So this is a 2 by 2 table. So this is a contingency table that we are talking about. So how do you want to measure degree of freedom over here? So because you have two categorical variables, so of course you need to take into account of your two categorical variable over here in the calculation of degree of freedom. So R over here refer to the number of rows. So how many category in your first variable and how many level in your second category variable. So in this case, your degree of freedom will be 2 minus 1 times 2 minus 1. So the degree of freedom is 1. So that's how you actually calculate your degree of freedom. So this is an example of a contingency table. So it depends on how many level are there in your variable 1 and how many level are there in your variable 2. So that will determine how huge or how big your contingency table would be. So for the independent test, chi-square independent test, your null hypothesis and your alternative hypothesis will sound something like this. The null hypothesis will always claim that there is no dependency of both variable. So it will be variable 1 is not dependent on variable 2. Whereas your alternative hypothesis will be claiming that there is a dependency of both of these variables. So it is just the same as like your t-test, like when you claim what is your null hypothesis, you always say that there is no difference. So therefore for your chi-square, there will be no dependency. So they always claim everything as neutral for your null hypothesis. So that's what you need to remember. Let's look at one of the examples to help you understand better how to calculate for your chi-square independent test. So let's look at this example. One plant can produce red or blue flower. If we suspect that the color is influenced by the type of fertilizer used, we can do the chi-square test as follows. So this is the information given, the statistic given over here for you to do your calculation. So as always, I will ask you, how do you know that is a chi-square test, is a chi-square test that you need to do? Because these are all frequency. These are all count. So it's not a continuous data set that you are looking at. So therefore, definitely it will be a chi-square test. It's the most appropriate or suitable test to be used. And how do you know that this is a the dependency test? Because it's asking you the influence of the type of fertilizer to the color of flower being produced. So therefore, is the dependency test of using chi-square. So for each data set, determine the expected frequency. The first step, determine what is the expected count for each of these cells over here. So what is your null hypothesis and alternative hypothesis? The null hypothesis will be there is no dependency of fertilizer used to the color of flower. So it's independent. And your alternative hypothesis will be it's dependent on the type. The color is dependent on the type of fertilizer. So the first step, we will need to determine the expected count. So how do you determine the expected count over here? It's quite simple. For example, I wanted to know for cell fertilizer A producing red color flower. So it will be 67 times 400 and divided by the total, which is 1000. And you get the number, which is 26.8. What about blue? It will be 933 times 400 divided by 1000 and you get 373.2. Fertilizer B producing red color flower, 67 times 600 divided by 1000 and you get 40.2. And the last one, fertilizer B producing blue colored flower, it will be 933 times 600 divided by 1000 and therefore you get 559.8. So let's move to the next step, which is to calculate the difference square, the difference between observed frequency and the expected frequency square divided by the expected frequency. I will encourage you to produce a table just like this to help in your calculation. So fertilizer A producing red colored flower, fertilizer A producing blue color flower, fertilizer B producing red color flower, and fertilizer B producing blue color flower. So these are all the observed frequencies. So you just copy and put it down. The sum is 600 samples. And these are the expected frequency that you have calculated in the first step over here. So just put it down over here and you calculate the difference. So negative 1.8, how do you obtain this? 25 minus 26.8 and you get negative 1.8. And square negative 1.8, you get 3.24. And with this, you divide with the expected frequency, 3.24 divided by 26.8 and you get 0.121. So do the same for all the rest and you sum up this number and 0.217 is the calculated chi-square. So you have done with your step 2. Now move to step 3 to obtain the critical chi-square value from the reference table. Refer to the Murdoch table and you will be able to get the critical value. But the question over here is that what is your degree of freedom over here to refer to? So the p-value is 0.05. So by default, we always follow 0.05 unless usually in your exam, so it will be mentioned like what is your p-value number. 0.05 over here. So the degree of freedom. The degree of freedom is number of row minus 1 times number of column minus 1. So how do you get this? So always refer back here. So how many row over here? 1, 2. 1, 2. So it will be 2 minus 1 times 2 minus 1. So your degree of freedom is 1. So refer to the table, degree of freedom 1, p-value 0.05, and you would get 3.841 as your critical value. So now we need to do our conclusion. So you do not need to memorize this. Always draw your distribution, and after that, pinpoint where is your critical value, 3.841, and shaded all the zone over here. And what is your calculated value? 0.217. So 0.217 fall within the non-shaded zone. So if it fall within the non-shaded zone, what will happen? So you fail to reject your null hypothesis. Fail to reject the null hypothesis, and therefore you accept the null hypothesis. So what does the null hypothesis say? The null hypothesis say that the flower color is not dependent on the fertilizer use. Independent, not dependent. There's a mistake here, so forget about this yet. So it's nothing to do with here. So chi-square less than critical value. So it's not dependent on the fertilizer. So that will be your conclusion. So that's all for the independent test. So I hope by now, so it should be quite clear to you how to calculate your goodness of fit and also independent test. Go to Spectrum and do the exercise. There will be 2 or 3 exercises that you can do to test your understanding for chi-square. Thank you.